Well, here in this exercise, we have a function of 5 variables, and we have to implement the function using only multiplexer 2. The 2 of this expression means that we have 2 selection variables. So we are going to have 4 possible input. So firstly, we are going to remember how a multiplexer works. If we have MUX2, we are going to have the following multiplexer. One output and 2 selection variables that I can, for example, decide that are X and Y. We are going to have all the possible combination of the inputs, and each combination is going to be associated with one input of the multiplexer. Remember that we have input of the multiplexer and selection input. They are not the same. I like to start with 0. So at the output of a multiplexer, we have all the possible minterms that we can form with the selection input multiplied by the associated input of the multiplexer. So we have 2 variables, so we are going to have 4 combinations and 4 minterms. So the output is going to be minterm 0 multiplied by the input 0, minterm 1 multiplied by the input 1, minterm 2 multiplied by input 2, and minterm 3 multiplied by the input 3. So when we have a minterms, for example, the minterm 0, imagine that X and Y are 0, 0. The minterm 0 is going to be 1. And we are going to have here 1 by the input 0. All the rest of minterms are going to be 0. So these inputs are not going to appear at the output. The output is going to be just input 0 in this case. So the basic use of a multiplexer to build functions is just connecting here ones or zeros to select the minterms of our function. In this function, imagine that we have only minterms 1 and 3, so we are going to have this. And in this case, the 0 and the 2 are the ones that are going to be 0. So here we have minterms 1 and 3. Well, so what is clear is that when working with multiplexers, we are interested in minterms. Minterms are going to be used to select the input. So we are going to start looking for the minterms of the function, because what happened here? We have the function, but given in conjunctive canonical form. And we need the minterm, so we need the disjunctive canonical form. This is the conjunctive canonical form, sorry. So the first step is to obtain the disjunctive canonical form. Where do we have the minterms? If here we have the zeros, in the gaps we are going to have the ones. So just checking the gaps of the first version of the function, we are going to find the ones, the minterms. that are going to be here: 4, 7, 9, 10, 16, 17, 18, 19, 21, 23, 24, and 26. I think that I'm not forgetting anyone. So we have a 5 variable function. So what we need is a mux5, but we are obliged to use mux2. Since we have to use a smaller multiplexer, normally we divide the function in smaller parts. So we are going to use an output mux2. Here we are going to have the output, and normally we select the most significant bit. That in this case, for example, we are going to use a function of a, b, c, d, e, and a, b are going to be our selection variables. So what happens now? We are going to build the truth table. With 5 variables, we have 32 combinations. I'm not going to write all of them. I'm going to write just some groups. For example, the first 8 combinations are going to go from 0, 0, 0, 0 to 0, 0, 1, 1, 1. Here we have from the 0 to the 7. The following 8 are going to be not like this, are going to be from 8 to 15. Now we are going to have from 16 to 23. And finally, from 24 to 31. And we have here all the truth table dividing in groups of 8 combinations. So why did I divide the function in 8? Because of the following. Here we have to connect to the input of the multiplexer we have created. So firstly, we have that a and b are equal to 0, 0. If we look at the truth table, we have that a and b are 0, 0 in the first 8 combinations that cover all the minterms between 0 and 7. So we can express our function extracting as common factor a and b in the combinations that we are interested in. For example, here we have that a and b are negated. So a and b negated, if we extract common factor, are going to multiply the minterms 0, 1, 2, 3, 4, 7. We have all those minterms in this interval, so we can include the minterms here. Minterm 1, minterm 2, minterm 3, minterm 4, and minterm 7. So all those minterms have to be covered by this input of the multiplexer. So we are going to connect another multiplexer another MUX2. And now we can select as selection inputs the following most significant bit, for example, C and D. And we are going to study what happened for all the combination of C and D. So the first combination of the new multiplexer is C and D 0, 0. That is both of them negated. If we extract newly common factor in this expression, we have here, we have here C and D negated, and we have here C and D negated. And if we extract common factor, we have E negated plus E. It's like this. And this is 1 because the properties of the Boolean algebra that we saw. So for the inputs C and D negated, we are going to have 1. We are going to start common factor little by little. For the following combination, we have C negated, D not negated. And we are here. C negated, D not negated. We have exactly the same. E negated plus E. And this is 1. So for this combination we have 1. And we are going to see what happens for the rest of the combinations. Here we have, here we have C D negated if we are here, and in this case we cannot extract more common factor than E negated. For this combination we have E negated, and for the last combination in which we have C and D not negated, we have E, because if you remember, in a multiplexer we have the minterms multiplied by the input. So these are inputs of this specific multiplexer. So now we have to continue with the function, and see what happens with the rest of combination of the first multiplexer. So for the second combination we have A negated B. A negated B, we are in this part of the table. This is 0, 1. 0, 1 we have in the following combination. So we have to extract common factor and build a new multiplexer, again with CD, and we have to connect to the input what we have here. And we are going to continue with the rest of combinations. For example, A B negated, that is 1, 0. We are here now, 1, 0, and finally we are going to have A and B. Both of them are going to be 1. So we are going to be here, and we are going to have more things. So we are going to connect one MUX2 to every input using CD, and we are going to connect to these MOOCs the main terms that we find here, here, and finally here. I'm not going to do all of this because it's long, but this is a method that we can use. It's a generic method that we can use always. In this case, the function is quite large, so it's going to be slow. But it's okay, it's right. We are going to start common factor, that is the same of dividing the function, the truth table, little by little, in some combinations that we are going to include in each of the multiplexers. Okay, this is a possible method, but it's not the more efficient. Imagine that the exercise asks to implement this function using MUX2, but using the fewest number of multiplexers possible. Because here we have 5 multiplexers, and we have to use the signal negated. As we are going to see later, to negate a signal needs a new extra multiplexer. So I'm going to explain you another method, another approach that is faster and more efficient from the point of view of the cost. I'm going to remove a lot of this screen because I don't have space, and I'm going to show you this method. So I have made some space. In this method we need to build the Karnaugh map of the function. So we have 5 variables and we need 2 Karnaugh map. So we are going to build the Karnaugh map. So we are going to divide the Karnaugh map using the most significant bit, as we saw in class, and we are going to use the rest of the bits to order rows and columns. So if we copy the ones of the minterms into the map, we are going to have this. And now we are going to start with the MUX2 in the output level, just as before. This is normal. To start with the last multiplexer is normal. It's the way to do it. So we have this multiplexer. In the previous example, we used the 2 most significant bits to divide the function. But now we have the Karnaugh map. So looking at the Karnaugh map, we can see that we can find another variable for which the function is going to be simpler. For example, if we look at the columns, I'm going to select this. Okay. If we look at the columns, we have that for B and C, we have that this combination is 1. All the column is 1, and this combination is 0. All the column is 0. In the other map, the same. So this is quite interesting in the case of the multiplexer. Why? Because if we select B and C here, when B and C are 0, 0, we are in those columns. For example, here, B and C are 0, 0. when B and C are 0, 0, we are here. And what's the value of the function here? Is 1. So this becomes really simple. Here we have 1, a constant. And when we have the other input, for example here, 1, 1, we have that the function is 0. It's always 0. So we can do this. It's much simple. In the other two cases, we don't have constants. For 1, 0 and for 0, 1, we don't have constants in those columns. So in those columns, we have to use another mux. And now we can select, for example, DA for this new level of MUX2. So let's see what happened. I'm going to select a new color. For example, for DE equal to 0, we are here. We are in 0, 1, 0, 1, BC are 0, 1, and DE are 0, so we are in this and this cell. So how can we express these values? In one map it is 1, and in the other map it is 0. If we pay attention to the most significant bit, we can see that in this case it's 0, and in this case it's 1. And it's just the opposite of the cell that we have to represent. So here, for 0, 0, we can see that the input can be E-negated. When E is 0, the cell is 1. And when E is 1, the cell is 0. So this input can be E-negated. For the input 0, 1, we are here. And we have just the opposite. We have the same value of A in each map. If A is 0, the cell is 0, and if A is 1, the cell is 1. So it's the value of A. We can use the variable A as input of this multiplexer. And what happens with the rest of the inputs? For 1, 0, we are here, and the input is 0 in both cases. And for 1, 1, we are here, and the inputs are 1s in both cases. So we have finished with this multiplexer. In the following multiplexer, the other multiplexer of the level, we can use another variables if we want. Sorry, but maybe it's complicated. So we are going to use the same ones, and we are going to proceed in the same way. But now we are in the column 1, 0 of the map, because we come from the combination 1, 0 of BC. So let's see what happens. For the input 0, 0, we are here, and the variable is the same variable, is the same, and the function have the same output of the value of A. So we have A not negated. For the combination 0, 1, we are here, and we have just the opposite. So is A negated, as we have with the previous multiplexer. For 1, 0, we are here, and we can see that the function is 1. And from for 1, 0, we are here. And finally, for 1, 1, we are here, and the function is 0. So in this case, just looking at the Karnaugh map and what happens in the columns and rows, we have obtained a more efficient representation of the function. Note that we still need e-negated. We don't have been told that we can have e-negated available. So we have to implement e-negated. E-negated is easy to implement with MUX2 because it's like this. So with a MUX2, sorry, MUX2, I meant MUX2 to 1. That is MUX with one selection input. So if we put here A, so we do this. When A is 0, the output is 1, and when A is 1, the output is 0. So this is e-negated. But in this case, we have to use compulsory MUX4 that are MUX4 to 1. So let's proceed. I'm going to explain you how to use a MUX4 to obtain a negated variable. I'm going to delete this, the negated A, because we are going to obtain this with the multiplexer. So we can disable the part of the multiplexer we are not interested in a really easy way. What happens if I put here 0? This is a constant. If I put here 0, these combinations are not going to be available ever, because for this one we need 1 and 1 here, and here we have a constant 0. So these are going to be combinations that are not going to take place never. So if I put here A, I'm going to do the same that with the MUX1, connecting here 1 and here 0. When A is 0, the output is 1, and when A is 1, the output is 0. And as I said before, we are not going to have never these inputs. In fact, we are going to connect this, for example, to 0 just for safety. I told you that we cannot leave the input of the combinational circuit and the logic gate unconnected. So as you can see, Karnaugh maps are really useful as well to find efficient ways of implementing functions with multiplexer. You can look for columns or rows in which all the cells are 1 or 0 to have these simplified versions. Of you can look. I'm going to give you another sample. Just give me 1 second. I'm going to delete this. So well, I have written a new Karnaugh map, of a 4-variable function, and I was telling you that as you have seen, we can use Karnaugh map to find selection variables for which all the row or all the column is constant, 1 and 0, and this is going to simplify a lot the implementation with multiplexer. But there is another approach in which we try to find variables that doesn't change, or that are that has the same value of all the cell of the column of all the row, and this is easier to see with an example. For sure, we have to avoid negated variables. If we have no option, we are going to include negated variables, but you have seen that we are going to use an extra multiplexer for each negated variable. So here we have to implement this function with MUX2 again. So following the previous approach, we have here that this column is constant, is 0 for all the cells. So following the previous approach, we can use A and B as selection variables. No? So we are going to try this quickly. So when A and B are 0, 0, we are in this case and we have 0. And for the rest, we have to check it. For 1 and 0, we are here. We need to implement this column with a new multiplexer. And now we use the rest of the variables. So we are here in this column. It's quite easy. The cells are 1, 0, 1, 1. So 1, 0, 1, 1. We use another multiplexer for this column, that is 1, 0, AB 1, 0, because we don't have a constant column, so we have to use a new multiplexer. And the values are, in this case, 0, 0, 1, 0, 0, 0, 1, 0, 0. And what happens with this column 1, 1? We can see that this column is the same as this. They are the same, 1, 0, 1, 1. So we can use the same multiplexer. So this is the implementation in this case. But I'm going to propose you a new implementation. And we are going to compare this versus the new one. What happens if we use CD as selection variables? I'm going to write again the map to have it cleaner, at least here. You may think that this choice is a mistake, because we don't have in the rows constants. In one row we have a constant 0 or 1. We don't have that. You are right, but we are going to see what happens. For the combination 0, 0, we are here. What is the output? 0, 1. I'm going to delete this as well. For this combination, the output is 0, 1, 1, 0. If we pay attention to the value of B is 0, 1, 1, 0. So for all the cells of the row, the value of the cell is the value of B. So we can do just this. What happens for 1, 0 and 1, 1 combinations? That we have again the value of B, 0, 1, 1, 0, 0, 1, 1, 0. So for 1, 0 and 1, 1 combination, we have again B. So another interesting approach is to pay attention to the value of the cells and the variables of the function. And for 0, 1, we are here, sorry. We cannot use B, so in this case we need another multiplexer. And now we are going to use the remaining variables. And they are 0, 0, 1, 0, 0, 0, 1, 0. Note that I'm jumping here from 0 to 1 because of the gray code, because after the 1 we have the 2 in the multiplexer. So be careful with that, okay? When comparing the value of the rows or the columns with the value of the combinations. So we have seen that in the second case, just pay attention to the variables. We have said one multiplexer. This can be complex because, you know, sometimes it's a matter of being ingenious. Try to look at the rows and columns in which we have constant values and try to look at this new approach. In both cases, we are going to have more efficient implementations that in the first approach, the generic approach of dividing the function in part, dividing the truth table. So, well, we have seen a lot of multiplexer. We are going to see more different things.